Today's lesson will be about the refraction of thin lenses as light travels through any kind of thin lens membrane. I'd recommend that you read the two little chapters that I have online there. It'll give you a much more detailed version than this video will, but I'll kind of walk you through a lot of the basics. A slightly different version of the class notes can be found online. And if you want to play around with some interactive media with regards to lenses, I'd strongly recommend that you go to this website here and just click on there, but you have to go to the Wednesday, June 3rd for class webpage. But you'll probably need to be in a browser that's not Google Chrome, because Chrome doesn't allow Flash anymore. So use a different browser. You should usually have one or two different browsers on your computer or laptop or mobile device anyhow, because some things work better than others on certain ones. So yeah, if you want to play around with it. But if you just want to watch this video, then that's good enough too. So the last video that you probably watched, maybe, was the last one I sent to you guys. And so that would be the refraction of light. And you did some calculations as well as to how you calculate the actual angles. And so that would have been Snell's law. But just a quick little recall, any light that travels from one medium into a different medium will suffer the effects of refraction. So in that case, this little example that's here is two beams of two lasers, red lasers that are traveling parallel to each other, but also parallel into this new acrylic medium. And so because it's acrylic compared to a gas, it's going to slow down in this acrylic and it's going to bend towards the normal line. So you can see that change in direction. If you look close enough, you can kind of see a little bit of reflection there, because there is going to be some reflection at the surface. It's not going to be 100% transmittance into the new medium. Some reflects back according to the law of reflection, but we tend to ignore that depending on what we're diagramming. So that was the last video. For this video, when we're getting into lenses, I need to first kind of talk about how when light travels from one medium into another. So if we have a quadrilateral, so that's basically a parallelogram, a square, a rectangle, as long as this two ends in which light enters into the new medium and exits that new medium, as long as these sides are parallel with each other, then any light that enters at whatever their angle of incidence is going to emerge back into the original medium at the same at an angle of refraction that is the same as the angle of incidence. So if this was 30 degrees as it entered in, it's going to be a 30-degree angle of refraction as it leaves. Likewise, just due to the way geometry works, since we have parallel lines as you enter and leave the medium, the inside angle, so the refracted ray as it comes in and bends towards the normal, this angle that you have there in blue is going to be the same as the new angle of incidence as it's leaving this medium. So when you enter and then leave back into the original medium, so that's the big thing here, it has to be the original medium, you're going to get lateral displacement. So in other words, the light ray is just going to be shifted by a certain amount, depending on how thick this medium is. If you have thin mediums, you're just going to have a little bit of lateral displacement, but otherwise the light is going to run parallel to its original path. So if you have a much thicker medium, the light's going to travel in that medium for a much longer duration, so greater distance, which means you're going to have greater lateral displacement, greater separation. When it comes to mediums that are thin enough, this lateral displacement is not really noticeable, at least not to the naked eye. You'd have to get, you'd be worried about that when you have high precision machines. But when it just comes to the bare naked eye, you would probably never notice this when it comes to thin films, like a piece of transparency paper or just any little thin piece of cellophane plastic. You wouldn't notice any kind of meaningful refraction. So when you get really thick stuff, you will actually notice that. So that kind of ties into our lenses. What happens if you don't have parallel sides? Well, it's not so much that you have lateral displacement, but you're going to have a shift, refraction, as you enter into the new medium and as you exit from that new medium. It's going to have refraction at both ends, and it's not going to emerge parallel to the original path. So that's what lenses are actually meant for, refocusing of light to a certain point. There's many different types of lenses. All right, we're going to look at two very specific ones. The double convex lens, well, when light enters from the left, for instance, it's going to hit a convex lens, convex surface. If it comes in from the right, it's going to hit a convex surface. So they call this one the double convex lens. This is otherwise known as a converging lens. The other one that we're going to look at is this hourglass shaped one. So this is the double concave lens, so otherwise known as the diverging lens. If light rays come from the left, it's going to hit that concave side. If light rays come from the right, it's also going to hit a concave side. So that's why they call it the double concave lens. Now there's hundreds of different variations of shapes that we can make for lenses, and most people, probably a good half the people that you know have glasses. If not yourself, you might have glasses, but odds are good you know someone with glasses. There's many different shapes of glasses. When I say shapes, I don't mean the actual frames. I'm talking about the actual lenses of the glasses themselves. They all have varying thicknesses depending on what the eye defect is. There's several different eye defects. We can talk about presbyopia, myopia, astigmatism. Some of them have more common names like nearsightedness, farsightedness. So depending on what the issue is or how severe it is will determine the actual curvature of the lens and how thick the lens needs to be. So we're not going to get into all those individual cases. We're just going to kind of look at just these two lenses in general. They're going to be symmetric, and it's going to be fairly simple. But the one big thing I need to point out now before moving any further is that all the refraction that takes place, light is always going to bend towards the thicker part of the lens. That's typically how it should refract as it enters into this medium. And that's how they're shaped. So your double convex surface lens is going to be your converging lens, and they're called converging lenses because all light rays that travel parallel to the principal axis when they enter into the lens will refract and go through the principal focus on the other side. So we'll call this the far principal focus. That is very similar to your converging mirrors. So that's when you had concave surface, but you had a mirror. So they would all reflect back to the principal focus. So it's kind of the same principle in its definition, but we are now dealing with refraction rather than reflection. Okay, and again, as you can see here, the light rays that are on top, they are bending down towards where the thicker part of the lens is. The light rays that are down below are going to bend up to where the thicker part of the lens is. You have refraction as you enter into the medium there, and you have a little bit of refraction as you leave the medium. So it refracts twice, once when you enter, once when you leave. And you end up with that pattern. Your diverging lens, boxes everywhere. Your diverging lens, similar to your diverging mirrors, all the light rays that travel parallel to the principal axis will diverge, in other words, spread out as they refract on the other side. When it came to the mirror, they would diverge and spread away upon reflection. But these ones are going to refract, so they're bending upwards up here, so they're going to bend towards the thicker part of the lens. So the light rays that are above the principal axis, they're going to bend upwards towards the thicker part, and they bend in such a manner as though they came from the near principal focus. So they line it up as though they came from the near principal focus. If light rays originated down below, they're going to also bend down towards the thicker part. No light ray from down below is going to bend upwards towards the thicker part above the principal axis when it comes to diverging lenses. So one thing to point out, there is refraction that occurs when it enters into this lens, and there's going to be refraction as it leaves this lens, right? And in both cases, they're going to bend away. It's not like you have a parallel surface. I can't say the angle which it enters in here is going to be the same as the angle it leaves at. Likewise for inside. But typically you're going to be dealing with thin lenses. So we tend to ignore the refraction as you enter and leave the lens. We just draw a dotted line right down the geometric center of the lens, and we reserve all refraction at the very center. Now, if this was, if you had larger lenses or just larger diagrams, you can actually have the refraction occurring at the entry and exit points. But since most of the time your lenses are going to be pretty small, you would just draw this dotted line and then ignore the refraction as you enter the medium and just refract only at the very center. It'll make the work a lot easier to do if you just follow that shortcut. So we have 6 cases in total. 5 cases are going to involve the convex lens, so the converging lens, and 1 case will be using the diverging lens. Similar again to your mirrors. We had 7 cases in total, 6 for the converging mirror and 1 for the diverging mirror. So it's going to follow very, very similar patterns. So I'll go through this a lot quicker than I did with the mirrors. So in case 1, we're talking about an object beyond the near double focal point of the convex lens. So this is for all objects that are, a little bit farther away from the lens than the actual double focal point. So there's 3 rules, and rule number 1 says any horizontal light ray, so any parallel light ray to the principal axis, is going to refract through the far principal focus. So it's going to bend down towards the thicker part of the lens, and in this case, it's going to travel through the far principal focus. Second rule is the easiest one to draw. It says a light ray that strikes the middle of the lens continues straight. So anytime you have a light ray traveling through the geometric center of a lens, you're not going to notice any discernible refraction. There'll be a little bit of refraction as it enters in, but then you have the exact opposite refraction as it leaves. Now again, this is assuming we're talking about a symmetric lens on both sides, top and bottom. So whatever refraction it did have there is going to get canceled out by the refraction there. So we just draw that one straight through without any visible refraction. Third rule says any light ray that's traveling through the near principal focus just refracts horizontal. It's going to refract parallel to the principal axis. And just like with our mirrors, where all 3 light rays intersect, that's where image is going to be. Except this time, our image is going to be where the refracted light rays are colliding, not the reflected. You'll notice we didn't draw any reflected light rays. Again, we ignore the reflected light rays when it enters into a medium. So image forms where all 3 of them collide, and then you state the image characteristics. SALT. In this case, my image is visibly smaller than my object. Right? If you don't believe me, there it is. So my image is visibly smaller than my object. My image is upside down, so my attitude is inverted. The location, whenever my object is beyond my double focal point, my image should be found somewhere between F and 2F on the other side, the far focal point and double focal point. And when it comes to lenses, when the image forms on the opposite side of the lens than the object, we call that a real image. So this lens can project an image on a surface. So that was first seen with pinhole cameras 1,000 or so years ago. I can't remember the actual date when some people discovered that you can actually project an image across the room. But the image, of course, will be upside down. So you need another lens involved to actually make it right side up. So as far as cases 2, 3, and 4, I'm not going to walk you through them piece by piece by piece, but I do have a little animation here, a little shockwave flash file that'll kind of get you most of the way there. Before I get into case 2, I'm going to point out that if this is my object, so I can make it slightly bigger, I can make it slightly smaller, I can invert it if I want. If I move my object further away from the lens, my image is going to get closer and closer. So the image is on this side. The image is going to get closer and closer to the principal focus. Now I can only move this thing so far to the left, right? But you'll have to trust me when I say if I move this thing much, 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 much further, the image is going to get closer and closer and closer to the far principal focus. If I move this at a great distance or an infinite distance away, the image would technically form at F. But if I move my object infinitely far away, the image height would be so small it'd be pretty much not visible. But that's a topic for later. So if I move my object to my double focal point right at 2F, this is where we have an image that forms right at 2F on the opposite side. This image will have all the same properties. It's going to be the same size. It's just going to be inverted. It's also going to be a real image. So very similar to case 2 with the mirrors, when we had an object that was found at the center of curvature, we had an image that was found directly right underneath of it. That was the exact same size, absolutely no magnification. So this would be your case number 2. Case number 3 is when you put the object between the double focal point and the near principal focus. It's going to create an image that's found beyond your far double focal point. If you move the object closer and closer and closer and closer to your principal focus, the image is just going to form much, much further away, to the point where as we approach your principal focus, your image basically forms somewhere near infinity. So you can see these lines are getting closer and closer, becoming parallel. The image is going to form way to the right, to the point where so this is your case number 3. And I will point out again, our image is now larger when we have case number 3. When I move to image number 4, if I put the object right on the principal focus, you'll see that the refracted rays are parallel with each other. Right? So no image is going to form with case number 4 with an object at your principal focus. I'm going to draw out case number 5. I'll show it to you now. Case number 5 says, well, what happens if you put your object between your near principal focus and your actual lens? So in that case, it's going to create a virtual image. Now I will draw this one out because it's not showing any of these imaginary lines. But this is your magnifying glass. Case number 5 for lenses is a magnifying glass. So if you're trying to look at, say, an ant, and you're looking through your magnifying glass, the real ant won't be visible. What you will see through the lens is the blown up version of it, right? You'll see the larger version of it. You will no longer be able to see the actual object. All you will see is the image, and it will be a virtual image. You won't be able to project this onto a screen, right? And so that would make it a virtual image. Magnifying glasses do not do that. So if I move this object closer and closer and closer to the lens, you'll see that the image also gets closer to the lens, but the image will always be found behind the actual object, right? Sometimes it might form at the principal focus, sometimes it might form at the double focal point. There's no real set location as to where that image is going to form, other than it will form behind the object. So that'll be a virtual image. So let's draw case number 5. I made the object small because now that I know the image is going to be larger, it's best to have that accounted for. So rules say that any horizontal ray, so this is a much shorter horizontal ray traveling to the right, the arrow indicates going to the right, should refract through the far principal focus. Now, due to that animation, we already know that we're not going to get an image form on this right-hand side. So what you would need to do is you would have to extend that light ray, because you need to know where all your refracted rays actually touch, and they don't touch on the real side, they only touch on the virtual side. So you'll have to use your ruler and just extend that light ray backwards as though it came from that far principal focus. Second rule says any light ray that travels through the center of the lens just keeps on going straight. You don't actually notice any refraction whatsoever. And hopefully you can tell that these two guys are spreading apart. And so therefore you'll have to extend that backwards behind the actual object. The third rule says any light ray that passes through the secondary focal point as it strikes the lens, well, no, didn't do that. It seems to have come from that near focal point. So the light ray seems to have come from that near principal focus. In other words, you line your ruler up with F, the top of the object, and the lens. So I made this line dotted because it doesn't actually exist, right? It doesn't have to be drawn in. That dotted line doesn't need to be there for right here. But the solid light ray here, this is the actual path the light is traveling. Once it hits the lens, it refracts horizontal as it passes the lens. So it's going to bend towards the thicker part. So that's why it bent downwards. The thicker part's below. Should have mentioned down here that, bends towards the thicker part. And again, this refracted ray won't touch either of these two, so you'd have to extend this one back as well. And when all three refracted rays collide, that is where our image should form. Little note, because this magnifies, this gets much larger, our image gets much larger. When you draw these for yourself in your own notes, it's not uncommon to make mistakes, precision mistakes. and not have all three of these guys collide and connect together. So just be really careful when you do your diagrams. Make sure you always have the light rays starting from the exact same point, because otherwise you're going to have points where some students will tell me, but my image formed over here, my image formed over here. At that point, I'd say, well, maybe get the math involved, which I'll show you in the next video if you want to find the exact location. Otherwise, just try to get your lines measured properly and make sure the lines that are supposed to be parallel to the principal axis are actually parallel to the principal axis. These short lines are kind of hard or easy to mess up because they're so short, they'll almost always seem parallel. So just keep that in mind. So this image is larger, it's erect because it's right side up. It's located just behind the object, in this case, beyond the near double focal point. But if I move this guy slightly, the object slightly to the right, this guy will also move to the right. So we won't be any more specific than other than behind the object. And of course, virtual. So the last case, and that's your divergent lens. So there is only one situation for your diverging lens, kind of like there's only one diagram for your diverging mirror. So again, they kind of follow similar patterns. So the three light rays that we're going to draw, any horizontal light ray, any parallel light ray to the principal axis, is going to refract as though it came from that near principal focus. Okay, typically horizontal light rays, parallel light rays are going to involve a principal focus, whether it's the near one or the far one, depends on which light ray we're doing. But this one's going to refract, so the refraction is always going to be towards the thicker part of the lens, so it's going to bend upwards, and it's going to refract as if it's actually started from down here. So you would just line this up. You need this dotted line drawn in because you need it lined up. This is the light ray that we're going to interact with. Second rule, second light ray is going to be the exact same. Any light ray that's going through the vertex, the geometric center of the lens, is just going to keep going straight. Whatever little bit of refraction you're going to have here is going to be canceled by whatever little refraction there, because again, we have a symmetric shape. And so it's the easy one to draw. Just draw a straight line through. That should be enough to know where our image is going to form, but then we're going to draw the third one for precision. The third one's a bit trickier. It says any light ray that is aimed on course for the far principal focus, right? So I was a solid line until I hit the center of the lens, because that's where we're going to show our refraction from. Once I get to the center lens, I don't actually need this dotted line here anymore. This is just where I was aiming. So I would delete it typically. But when we get to the lens, the center lens, our refraction should be horizontal. It should refract parallel to the principal axis. Okay? It should bend upwards because we're still above the principal axis, so it's going to bend towards the thicker part of the lens. Technically, if our object is drawn upwards and we're doing a divergent lens, you don't actually need really anything down below. Right? We're not going to bother drawing anything down below. So this green light ray, the refracted light ray, obviously isn't going to hit the pink or the purple, so we're going to have to extend that one backwards. So I got rid of that dotted line there just to help with the confusion. I don't need that incident dotted line. So let's extend that guy backwards. And where all of my extended refracted light rays, right? I'll even include the purple one for that, but where the pink and the green and the purple all go through the exact same spot, that's where our image should form. And if you have a divergent lens, you should have a smaller image every single time. It should be erect. It should be found, so in this case, it's between the principal focus and the actual lens. But if I move this object to between the principal focus and the lens, the image is still going to form in front of the object. So we'll just call it, as a general sense, it's going to be located between the object and the lens. All right, it doesn't matter where this object is, up close or far away. This image is going to be found somewhere between the object and the lens, but the image will never move. Oops, wrong line. The image will never move past the principal focus. You will never see the image over here. The image is always going to be between F and the actual lens. And of course, it's virtual. You'll probably notice a pattern. Anytime you have an erect image, it's also virtual, right? Likewise for your mirror cases. Whenever you had an erect image, it was also considered virtual. You cannot actually project it onto a screen anywhere. So those are your cases. If you have a moment and you feel like watching both of these guys, I'll let them play. So essentially, we just went through this, and you'll see that no matter how close the object gets to the lens, the image is always going to be smaller, and it's always going to form between the object and the lens itself, as that animation shows. Top light ray, because the height's not changing for the object, the top one doesn't change at all, right? The top light ray, but the others do based on the geometry. For this converging lens, it's only showing 2 of the light rays, but you can see all the different cases. As it gets closer and closer and closer to the lens, you'll see how the image changes from going really small to ridiculously large to virtual. So on that note, I'm going to end the video, try some of the problems, try some of those diagrams, and we'll look at using those mirror equations, which are also known as the thin lens equations, for the next video. It won't be very long because you should have seen the math for that already.